Thank you all for coming today. It's not new, so I wanted to get our speaker off over here to hear about it. My name is Paul Clemson. I'm the section president here for the Columbia Section ASCE, and I want to welcome you all for coming and taking the time out lunch hour to join us. A couple things before I get into introducing our speaker today. Just to let you know, Engineers Month is February. Engineers Week is the last or second to last week of February, and I don't have the flyer here, but I know I posted it on our webpage and also our last newsletter. But the Engineers Week banquet is scheduled. I think it's the 22nd of February this year. They're still accepting nominations for Engineer of the Year. We haven't had a civil engineer representative since 2009 when we had Ben Folk represent us in open ed. So just keep that in mind if any of you all had some nominations. The paperwork's on the website, and it's also attached, I believe, in the last newsletter. So without further ado, I've got Matt LaCome here, Meier Engineering with me. He's been on a project for the past year or so almost, if not even a little longer than that, out at Hanford. It's got a pretty long title, so I won't bore you by reading the slides, but I'd rather him just tell you exactly what it is he does. Thank you very much.
Yeah, thank you. Thanks, Paul. Hello, how's everyone doing today? Like Paul said, I work with him at Meier. They have leased me out to the site, though, and I've been out there since September of 2011, so going on a year and a half. And I've been involved with the project that I'm going to be presenting since then. Just a little bit of background on myself. My training is a structural engineer, and I touch on some civil work as well. But with this project, I've been involved. I'm the project engineer for Phoenix Enterprises on the project, and we're working with WCH, who's the prime contractor on the project, and then there's a team of companies that we're working with. And I'm going to sit down as I go through the presentation. I just want you guys to open up with any questions you might have. Stop me as I go through it. I'll open it up to questions at the end as well, but please, we'll just talk some engineering stuff. So the project that I'm working on, the formal title is the 308A TRIGA, 309 PRTR and FEC, and the 340 vault removal. And so those are the three major tasks of the project, and that's what we'll start with there. Before I get going into the project, I just want to mention a few people that I'm working with. The contract is with Phoenix Enterprises, and Teresa Schatz and Luke Self are the representative from Phoenix. And then, like I was saying, there's a group of companies, LVI, Barnhart, Meier, Cutting Edge, and MHF that all support the project with engineering as well as performing the work along with the design. So it's a design build project, and we work together as a team on it. They are. It's a small business that won the contract from with WCH. So yeah, they are a small business, and then they grouped up with LVI. LVI's doing a lot of the work, and then Barnhart, they're hoisting and rigging. They're doing all the heavy lifts out there for us. Meier's providing engineering support, and then Cutting Edge, we're doing a lot of wire cutting on concrete structures, and so Cutting Edge is doing the cutting, and then MHF is doing the waste packaging design for us. An overview of what we'll be talking about. Number one and foremost is safety out on site. That's the highest priority for us, is to provide a safe environment for the workers and to get the work done. We'll look at codes and regulations. We're under a lot of different regulations and codes that we have to adhere to. And then as we developed, like I said, we started the project in September of 2011. And as we've gone through the project, we're still doing design. So it's the design evolves and continues as the work, up until we're getting the work done. So design reviews that have been substantial, and I'll go through some of the reviews that we go through. And then the work itself, one portion of it, even though it's not in the title, was waste site excavation. So we went out to clean up some of the waste sites out there, and we've pretty well wrapped that part of the project up to date. And then the bulk of the work is the 308 TRIGA reactor removal, 309 FEC removal, and then the 340 volt and 309 PRTR removal. And to date, we did disposition the 308 TRIGA reactor last year, as well as the 309 FEC. With regards to safety, we have a site safety plan, a HASP that we all adhere to, and then on top of that, we have engineering and administrative controls. We work to an IWC program, which is an integrated work control. So we develop work plans as part of the design planning effort. So each task that we do goes through the IWCP program, and we develop work packages prior to implementing and doing the work. At the beginning of the design, we started with engineering design hazard identification program, and we had workshops. We brought in WCH engineering, WCH management, as well as DOE reps, and went through and tried to mitigate as much of the risk that we could on the hazard identification up front as part of the design. And then, being Hanford, we have thorough radiological controls and contamination spread prevention. So getting into what I was saying about the IWCP, each activity goes through a planning stage. Once we get substantially complete with the design, then we start looking at developing work packages. And the work packages vary in complexity, being the lower end is a craft work package, and then step-by-step task instructions with a type 1. So these are just some samples of some of the work packages that have been developed for parts of the work. Went a little fast there. Sorry about that. Getting into the design codes and regulations, these are just some of the highlighted codes that we follow and adhere to during the design. Some of the significant ones that you guys are probably well familiar with is ASCE, IBC, ACI, AISC. Those are standard design codes. And then being on site, we work to the WCH General Design Criteria, the DOE Hanford Site Hoisting and Rigging Manual, the ERDIF Acceptance Criteria, and I won't read through all of these, but you get an idea of the regulations and codes that we're following during design and implementation of the project. And for each of the parts and pieces of the project, the design, again, goes through thorough review cycles. Internally, we have management review the designs. We do multiple design reviews as a group, and then we turn it over to WCH Engineering and Management, and they do reviews on the design as well. And then it goes on to DOE for transportation and waste packaging and overall review as well. And one of the review cycles that has been implemented for this project with some of the more complex parts of the project is what's called a TRG review, which is a technical review group. It's an independent group of engineers and managers that come in as a peer third-party review that reviews the designs as well. Again, I had mentioned previously about the design hazard identification workshops, and we look at structural integrity evaluations of when we get into it, what we're doing is we're taking structures and on the 308 and 309, we're removing the core, the reactor cores, and dispositioning those at ERDIF. So in doing that process, there's a lot of structural integrity evaluations that go into it. a lot of soil stabilization with the 340 vault that we'll talk about a little bit. And then obviously hoisting and rigging is a big part of it. Barnhart has a lot of involvement with the design of the lift systems. And then once we do the lift, then we're going into waste packaging and macro encapsulation. Once we've got it on the transport vehicles, then it's, we have to look at transportation analysis, getting it on the highway, doing securement system designs to make sure the package is secure to the vehicle, as well as the waste packaging so it meets DOT regulations to get the packages on the highway. And then once we get it on the highway, we transport the package out to ERDF, and we do analysis on the offload as well to get it in its final resting spot. The project is located at the 300 area, so it's approximately about 25 miles away for the transport on the highway. So we just did the 308 at the end of last year, and it was a 12-hour drive for us because the transport vehicle's going. You can walk with the vehicle. The guys that are doing the transport are walking alongside. We've got guides and people, flaggers and stuff walking with the package as it goes down the highway. Problems with the computer. Okay, perfect. Um, One of the first waste sites that we excavated out was called the 321 waste site, and this is a excavation drawing that was developed at Meier, and it shows the extent of the excavation in plan view. And so we've got a ramp coming down into the pit, and there was some demolition down inside the pit of existing concrete structure. And this was a several tiered excavation. We went down, you can't see it exactly on the plan view, but we went down to the bottom of the pit around 45 feet depth. So was the excavation. So we had to put in benching, and actually this large section up here is a bench that we put in for the actual equipment to get down to the lower excavation. So we started up top, and we expanded it down, put in a working bench, and then went down and excavated down. And this was our primary removal ramp that the trucks would drive up and down into the pit. Another waste site that we excavated was the 340 waste site. And we'll talk more about the 340 as we talk about the vault. But the 340 waste site, the 340 vault was located right here, and that structure is still existing. It was an underground vault structure that we'll talk about a little bit later, but there was an associated waste site as well that we had to excavate out prior to getting into the vault removal. The TRIGA, some of the highlights of the design. The lift weight was 250 tons, and it was a monolith with dimensions of 11 foot 6 by 17 feet by 18 foot 6. So it was a big chunk of concrete pretty much that we removed from underground. And in order to get to the monolith, we had to excavate out around the 308 and do an excavation for that as well. We had a design assumption of 3,000 psi from historic drawings, and we did go in and validate that assumption by doing non-destructive testing of the concrete to validate that the existing concrete was indeed 3,000 psi. And I believe when we finished the testing, it came out that the existing concrete was well above 3,000. It was up in the range of 4,500 to 5,000 psi. And then we, again, like I said, we have to do the transportation securement system design criteria, and it's 49 CFR 393. And one of the criteria of getting the package up on the highway is that the dose rate limits are within these parameters, being 200 millirem per hour on contact, and then the 10 millirem per hour at a distance of 2 meters. So once we get through with the design, then we go into actually implementing the design into the means and methods of how we actually do the work. And so, like I said, for 308, we had a ramp pit excavation. There was some excess concrete sticking off the sides of the monolith that we had to do wire cutting to remove. And then we had to prepare for lifting the monolith, assemble the lift system, then do the actual lift, position the monolith on top of the transport vehicle, the Goldhofer. Once it's on the vehicle, then we went into packaging and securement, and then transport to RDIF and offload. And the means and methods for the monoliths will follow kind of the same scenario. There's some uniqueness to each one, and we'll highlight some of those unique qualities. So here's a plan view of the excavation pit for the 308 removal. Again, we had to build a ramp down into the pit. And because this transport vehicle was staged down at the bottom of the pit, it required that we did quite a more extensive ramp than what you saw on the wayside removal, because with the waysides, we're just using equipment that can travel at a steeper grade. With the transport vehicle for the monolith removal, the grade was maximum 5%. So we ended up, because of constraints of other projects kind of boxed us in, we ended up having to come in with a ramp, kind of a nice shape like that to get down to the bottom. And then the trigger reactors sit right down here at the east side of the excavator pit. Once we got the excavation completed, then we were into preparing the monolith for removal. Again, we were doing some wire cutting as well as core drilling. The system that we used to lift the monolith for the 308 was some lifting haunches that were on the east and west side on the corners here. And so we drilled in a total of 24 high-strength maxi-bolt anchors at each of the corners. So there was 6 at each of the 4 corners that were drilled into the monolith for removal. And then this gives you an overview of the lifting system and the transport vehicle. So over here, it's maybe hard to see from where you guys are at, but this was the lifting haunches here. We had 2 haunches on the east and west side, and then the lifting beam was installed. And then these were pull-up gantries. They're a jacking system that lifted up the structure. We installed these tracks underneath the pull-up gantries, because once we lifted it up, we had to move it and position it over the transfer vehicle. Once it was on the vehicle, then it was packaging it and securing it. The packaging was an IP1 soft-sided packaging system that MHF designed, and then the tie-down securement was designed by Barnhart to anchor the package to the vehicle. We had a transport frame and locking system to hold it in place during transport. Out on the highway, we had a predefined travel path haul route out to RDIF, and one of the early on design considerations was overhead utilities. In fact, for the 2 larger monoliths, the 309 and 340, we actually had to have work done to remove certain interferences. Overhead utilities were either put underground or abandoned in order to remove potential interferences with the travel path. So you can't really see it, but on the right-hand side here, we have all the utilities, overhead utilities identified, clearance sites, and what we needed to do to remove those interferences. And then for the 308 offload, it was a fairly simple design. It was, again, using the pull-up gantries. We didn't have any tracks or anything because the vehicle just positioned the monolith in its lower position to the position, its final position, and then we just built up cribbing and put in the pull-up gantries, and then used the same lifting beams to lower it down with the haunches down to the ground. Any questions on the 308? That kind of wraps up the 308. The next part was the 340 vault, and the 340 vault we're still working on. almost complete with design. We're right about 95% done with the complete design. We've got a couple more comments that we're addressing. We've excavated out and we're getting ready to start doing the work on it. Some of the highlights for the 340 is the lift weight's 1,100 tons, which is substantially more than the 250 of the 308. It's a very large lift, and the transport weight is 1,200 tons. So we're adding another 100 tons just in the grouting of the base and the securement and anchor system and transport frame. We're adding another 100 tons to the transport weight. The vault dimensions, it's 29 feet wide, 40 foot long, and 25 foot tall. So it's a large concrete structure that will be lifting up and placing on the transport vehicle. Again, the historic drawings have indicated that the concrete was 3,000 psi. And again, we had to validate that with non-destructive testing methods on the existing concrete. And then one of the big considerations, because it's down and it's an underground structure, was the existing soil design parameters. And Shannon Wilson actually helped us develop a soils report for the 340 vault removal. And then following the same format with the transportation securement design and the dose rate limits to get it up on the highway. Yes, on 308 it was not. 308 we didn't find any soil contamination. 340, like we highlighted early on, we had a waste site that we excavated out to get down to excavate the vault. And now that we've excavated the vault removal pit, which we'll show you here in a second, there is contamination down there, and so we've had to bring in clean fill material to plate over the contaminated soil in order to do the work down in the pit. But then part of the design and part of the means and methods is we're going to be tunneling underneath the vault to get the lift system in place, and so there's going to be considerations of contaminated soil as we burrow in underneath as well. Again, means and methods real similar. We've got the ramp excavation and vault prep. And then we'll highlight some of the design here with the initial load transfer. Once we had it excavated out, and we'll show you on subsequent slides, the soil conditions were such that we had to do a two-stage transfer of the load from the soil to the lift system, and I'll show you what I mean here in a couple slides on that. And then assembling the lift system down in the pit and preparing the grate under the vault and installing the IP1 pan. As I mentioned, I showed you on 308, the lift system we had for 308 is we picked up the vault and then we moved it over on the track system and lowered it on the vehicle. For 340 vault, we're picking up the vault and then we're backing the vehicle underneath it and lowering it on the vehicle. So we've got to prepare the ground once we get the lift system in for that vehicle to come in underneath the vault. And then we're going to lift the structure, do the final load transfer. Excuse me, I kind of got backwards my flow chart here. Final load transfer, lift the structure, prepare the grade under the vault, position onto the gold hopper, and then the packaging and securement and transport to RDIF. This slide shows the actual final vault removal ramp and pit excavation. So we had the waste site, and it was in this area here. And there's the vault there. And again, because we're using the gold hopper transport vehicle, a different configuration, obviously, because of the weight difference between the 308 and 340. But because of the grade restrictions of the maximum 5%, we had to design a ramp from the bottom of the pit up. And then because of site conditions, we have to do a switchback turnaround. So we're coming up, this is to the north, and then we're doing a switchback down to the south for getting out to the highway. So it's quite a substantial ramp that we have. And we've completed the ramp, it's all done, and it was fairly lengthy actually when it was all said and done to build the ramp. The vault preparation, these activities on vault preparation are currently ongoing. This is where we're at in the process. We've installed fall protection up on top of the vault because we've got to put some securement plates to anchor the vault together. So we're getting ready to do that. And we've got the fall protection in. And once we have plates over pipe penetrations, will be there is some hot spots because there is some contamination when we did some of the wire cutting. We exposed some contamination, so we're going to be doing some shielding with plates on the sides of the vault. And then, like I said, up on top, we're installing some cover block stabilization plates and installing some hatch covers with tank stabilization braces, because internal to the vault are storage tanks that have been filled with grout that have to be secured during transport. And then as we're doing all these activities, we're monitoring the condition of the vault, because it's the design of the vault was to be underground. The cover blocks are removable from the top. And so as we're going in to lift this large structure up, we're going to be monitoring the condition of the exterior walls and the slab footing that's underneath it to make sure that nothing's going on that's not anticipated as far as movements. And then once we get it all ready for lifting, we're going to be applying a polyurea coating for macro encapsulation around the four sides and the top of the vault. And this kind of gives an indication of what I was saying about the cover block stabilization and internal tank stabilization. So we've got the vault. This is looking down on a roof plan view. And we've got these removable precast cover blocks, concrete cover blocks that form the roof. Again, these being removable, they don't lock the structure together, and you don't get that diaphragm action for the transport analysis. And so what we've done is we've come in and we're going to be putting in these plates and welding them down around the areas to secure it all together. And then internal to the vault are these tanks, and so we've got these cover hatches that we'll be installing stabilization posts to secure the tanks down as well for the transport analysis. The initial load transfer that we have to do in order to get the lift system in, what we're doing is we're going to be auger boring underneath the vault and installing steel casings. And this is just a snapshot of the auger boring equipment that we'll be using to push these casings underneath the vault. And again, once we excavated out and we had the geotech engineers come and evaluate it, it was determined that we couldn't just put in the lift system, that we had to do an initial load transfer. And we came up with the design scenario to install steel casings to support the vault while we install the lift system. They're 36-inch diameter steel pipes, a half-inch thick steel. Once we get the casings in place, in order to clean out, because we're going to just jack these casings in, push these casings in with an auger bit to clear them out, and then we'll be filling the casings with concrete. Once we get the casings in place, then we've got to excavate the soil around the casings in order to get the lift beams in, and we're going to do that excavation with a remote controlled mini excavator, and this is just a photo of that piece of equipment. So we'll be using this equipment to clean out the soil from around the casings in order to get the lifting beams in. This gives you an overview of the lift system for the vault. There's a total of 7 lifting beams, primary lifting beams that will go underneath the vault, and then we've got the transfer girders and transfer beams that the lift beams lock into. So here's the lifting beams, and then there's a transfer beam that ties into this large 8-foot tall girder. And then we've got it again with pull-up gantries for the jacking system, for the lifting system. So the 8-foot girders span across, and there's a total of 2 pull-up gantries on each corner. So there's a total of 4 pull-up gantries, or total of 8, pull-up gantries to lift the vault up. Once we've lifted the vault again, we'll be positioning the Goldhofer transport vehicle underneath the vault. So this gives you an indication of the different configuration for the vehicle compared to the 308. This transport vehicle is a 24-line double-wide gold hopper. So it's got 24 axles going down, and then it's a double-wide as well. So it's substantially larger than the 308 transport vehicle. Once we've got it onto the transport vehicle, then we'll be installing the soft-sided covers. And this is just a plan view of a design of the packaging that we'll be going over. And we're still getting a revision on the packaging because implementing this large of a package, it's 40 feet long just at the top. So this dimension from here to here is 40 feet long, and then it's 30 feet wide. And so when you lay this thing out, it's like a football field. And trying to pick that up and get it over the top of the ball is a challenge. So we've gone back to MHF, and they're working on a revision right now where we're going to segment this up. So instead of having one giant package that we try to pick up and place on the ball, we're going to come in and do 5 individual pieces. So we'll set the top, and then we'll come in and set the sides so it's more manageable. And even then, we're going to have to use a crane and spreader bars and everything just to get those size pieces in place. But trying to get the overall package all in one shot was just too much of a challenge. So we've gone back to the design and are going to segment it up into pieces. Once the packaging's done, then we go into the transport securement. And again, we'll be, Barnhart's going to be implementing this with tie downs, and there's this large girder beam that comes over the top of the ball and then ties down to the transport vehicle. And then there's also horizontal and lateral restraint lugs that lock it into the transport vehicle. So the girder is holding it down vertically, and then for the lateral and longitudinal, there's restraint lugs that's locking it all into place. And then it's kind of a recurring, once we're on the highway, we've got to get it out to RDIF. Same challenges there, even more so with this one, with the overhead interferences and dealing with that. And WCH actually has had all the interferences already removed. And that kind of gives you a little highlight. I don't think it's too clear from where you guys are at with some of the overhead line utilities. And for the 340 vault, the RDIF preparation is a little more substantial just because of the weight and the size of it. And so we have to coordinate with the RDIF personnel in order to prepare the site for the offload. And we'll be installing some crushed rock bedding just to allow us to offload that onto the ground. And then the offload, we'll be using the same system that we used to lift it with the 8 pull-up gantries and the 8-foot girders, and just having the gantry set up on cribbing to lower it directly to the ground. And then that just shows another picture of the RDIF offload. Any questions on the 340 vault? For the 340? That's for working days. It's kind of an interesting deal because the design's ongoing and certain things are changing during the design as well as we go in to implement things. I mean, we're finding out things like the soil conditions as we excavate out. We're finding out things about the actual dose rates as we do some of the wire cuts. So that's a really moving target because we continue to find things that weren't planned for, that we have to accommodate during. We start implementing the means and methods, and then we'll find a condition that we weren't aware of, and so we're going back to design. So that's a moving target, really, to be honest. And then the last one is the 309 FEC and PRTR removal. And these are some of the highlights. The 309 FEC has been dispositioned. We did that. We finished that project or that task last summer, and it was compared to some of the other ones. It was a pretty small piece. It was only 55 tons, but it had its uniqueness as well. And I'll show you. I think I've got 1 or 2 slides on that one. And then the dimensions of the FEC was 4 foot by 4 foot square, and then 32 foot long. So it was a long, slender piece that we removed. And then the 309 PRTR lift weight it's real comparable to the 340. It's 1,100 tons, but the dimensions are different. The PRTR reactor is a 26-inch diameter bioshield by 21 feet tall. So it's a cylinder that we're actually removing from what's called the containment vessel. And again, with the 309, we had existing soil design parameters that were developed. Shannon Wilson provided a soils report for us on that because we've got to do some site preparation in order to get the Goldhofer vehicle up to where we're going to be removing the structures. And the same thing goes with the transportation securement as before and the dose rates to get it on the highway. Yeah, so this is a slide showing the FEC removal. Again, this was a long, tall, slender piece, and what we did with this one was we put it in a steel IP1 container. So we got the FEC into the container, and then we grouted it full. And so that kind of shows the evolution. And when we did it, we had the container standing vertically 32 feet up in the air off the transport vehicle. And they had Barnhart had designed a system where they could lock it in place here so that we could get the FEC into the box, grout it, let it cure, and then lower the system, lower the box down to the travel configuration, which is laying down flat. And for the 309 PRTR, similar flow chart for the means and methods, preparing the PRTR, which we've been ongoing, getting ready to do the pick, site preparation, which we have to do for getting the vehicle up near the removal site, shoring and concrete demo. This one's a little different from the other ones because the structure that we're removing it from has lots of different elements, structural slabs and such, and we're cutting a big chunk of that structure away, and so we've got to come up. We designed a shoring system to be installed prior to doing some of the slab cuts. Installing the lift system, and then lifting the structure, positioning it on the Goldhofer, packaging it and securing it to the vehicle, and then transporting it to RDIF and offload. The preparation for the PRTR, one of the first tasks that we took on was removing interferences and removing piping from underneath the reactor. And then that's just a spaghetti of piping that was down there. And we've removed a substantial amount of it. We still have a couple of miscellaneous pieces to remove, but a substantial amount of the piping has been removed. And then also we've done preliminary core drilling to prepare for the concrete cutting to cut the reactor free from the supporting structure. And we're getting ready to start installing the structural shoring and putting in all the shoring columns. And once that's done, then we'll be going in and cutting concrete supports, installing the lower lift frame, sealing all the penetrations in and out of the reactor on all sides, and then also applying a polyurea coating for macro encapsulation. A plan view. Meier came up with the structural shoring plans and details, and so this gives you an overview of the removal process or the removal. This is at elevation 0. Again, the reactor goes down below grade, and so this slab here for the most of this slab is 5 foot thick concrete. There's a section of smaller concrete, but the bulk of this concrete slab is 5 foot thick, and we're going to be cutting a really irregular shape out of this concrete slab. And the reason that we came up with this irregular shape was because we wanted to minimize the amount of structure that we removed. And you can see the outline of the lower lift frame that kind of looks like spider legs coming out in all directions. And so we needed to clear the lift system, lifting beams, but minimize the amount of cuts. So that's, people have all, come up, that's quite an irregular shape, but there was some reasoning behind it where we didn't want to cut a lot of the concrete away because we have to put in these structural shoring columns where we needed it for supporting the lift system, but we wanted to minimize how much we had to do on it. So it's somewhat of an irregular, quite a few cuts being made to remove that concrete. And it gives a little bit better detail of the lower lift frame. So once we've got the concrete slab sections that we're going to be removed out, then we'll be installing the lower lift frame to underneath the reactor to lift it up. And the lower lift frame has 4 primary supports. And the next slide will show us a little bit more about the lift system. But there's four primary points of lifting, and then these are just secondary bracing pieces in there. It's got a center hub that just that piece right there. These are W36 by 395 beams, and so just this center hub right here weighs quite a few tons. It's quite a massive structure to lift that 1,100 tons up. In fact, in order to even get the lift system in order to get the lower lift frame in, we're having to construct a working platform down below the reactor just to get the parts and pieces in to do the lift. And so part of the design was coming up with how are we going to, we designed this lift frame, well, how are we going to get it into place? It's a small space down there in relation to the pieces that we're putting in, and so we had to come up with a work platform in order to actually get the lifting system into place. And this kind of shows you the overview of the lift system and the and how we're going to do it. So what we're doing is instead of using the pull-up gantries that you saw on the 308 and 340, what we're doing is we're using strand jacks, and there's a total of 4 strand jacks, and each one of those strand jacks can pull 450 tons. So the capacity is 1,800 tons with this lift system, and we're lifting 1,100 tons. And then the supports for those strand jacks are large steel girder beams, and it's kind of just stacked up. And then you can kind of see a similar section there where we're using the same 8-foot girders that we use for the 340 volt, we'll be using for the 309 lifting system. This lifting system is a little similar to 308 where we're installing tracks. And so we'll be lifting up the PRTR in this position, and then the transport vehicle will be staged over here, and we'll be rolling this down these tracks or moving this down these tracks to position it over the vehicle. Once it's on the vehicle, again, we go into the packaging and securement. And again, large girders, very similar to 340 volt for the vertical restraint. And then we've got locking pins for the transverse and longitudinal. There's not a lot of detail here, but they're large rods that will be locking it into the vehicle. And then it's kind of repeating as far as the haul route out to RDIF with interferences that we've had to address. And then the offload is a little different for 309 as well, because the lower lift frame will actually go and get dispositioned at RDIF with the package. And so we're having to install actually a 30-inch thick CDF pad over at RDIF in order to accommodate lowering the structure onto the ground, because the lower lift frame is concentrating all that load onto that frame, and the soil parameters out there, they just can't make it. So we're having to pour a pad out there in order to spread the load out to the soils. And then this kind of goes through that scenario as far as the prep goes. We'll be putting in the CDF pad. This gives a little bit of detail of that prep. And then lowering, using the strand jack, same as lifting it, we'll be using the strand jack system to lower it down onto that CDF pad. For the girders, those are plate steel girders, and one of those girders weighs like 30 tons, just one of them. Oh, what grade of steel? It's 50 KSI steel on that, yeah. Any final questions? That's what I got. The total base cost was around 19 million, and we've added scope as we've gone through it. I don't know where we're at right now, but the total base cost was around 19 million. Yes, sir. Yeah, the 300 area is being reclamated. In fact, recently the city of Richland has started to bring in new utilities, new electrical utilities out there. And so the plan is to reclamate the land and turn it over to the city of Richland for commercial and industrial development. So that's the end result. So we're having to disposition and there's been a lot. I've been there about a year and a half, and the amount of structures and demolition that's taken place, not just on what I'm involved with, but the overall site at the 300 area, it's truly amazing. And just a couple weeks ago, we were driving around the site, and the waste sites and how much has been cleaned up. It's incredible. It's really great. Yeah, that's our project here. We're planning on having it done this spring. Actually, I mean, we're right there getting the 340 vault prepped and getting that ready to go. We're planning on having that out this spring, and then 309 is working right at the same time. So for our project, we're looking at late spring to getting our part done. As far as the overall 300 area, I don't know the exact schedule, but I'm thinking it's somewhere around 2014, 15-ish, somewhere in there. So they've still got a couple more years of work out there, to the best of my knowledge. I don't know exact dates on that though, but somewhere probably within the next 2 to 3 years it'll be completed. And then as far as turning it over to Richland, I don't know too much. I know that Meier actually is helping the city of Richland establish some of the utilities out there. Steve Strickland has came out to the site several times and met with me, and they're starting to reroute utilities out there and turning over utilities. So it's coming. There's still some work to be done. One of the biggest challenges on site after this project that's left out there is what's called the 324 building, and it's a highly contaminated structure, and it's that's going to be a real challenge. So there's still some big challenges out there, but we're making progress. Anything else, guys? Well, thank you for listening, and I appreciate you guys inviting me to come. Appreciate it. Thanks, Paul.
On behalf of the Columbia Section ASCE, there's a
Oh,
little
thank
water
you.
jug.
Perfect. Great.
A couple quick things just to let you know. I have some flyers I'll leave right at the front in case any of you are interested in this is actually sponsored by the Structural Engineers Association of Washington. It pertains to TC20, TC25 training. I don't know, I didn't know what that meant when I first saw this, but then I got looking into it and I was like, oh, yeah, there it is. That's California down there. What this has to do is for if you're a commissioner or an engineer and you're interested in looking at buildings and seeing this is the training that you want to get. SAW is putting it on. It's very reasonably priced. I don't know if anyone's interested, but I was going to leave those at the front, so I'll throw that this way. If anyone squared up with us, just pin down either me or Teresa afterwards. Most of it taken care of, but produce our treasure today. Bucks out. And also, kind of just to give you the taste for what's coming up, I have some speakers confirmed for March and for May. And in March, we're actually going to have President elect for ASCE Nationals coming into town. President, we just missed him last year by a little bit. He's actually from Water District in Portland, he's from last year. Civil engineering at CNC always everyone has a letter in there, but that'll be exciting. That's in March, and then in May, we're going to have a joint meeting with the Yakima section. CPA Brands is going to be on the city side. Really having a great speaker come for that one. I invite you all to attend. They're $400. Facility with John Magus. That's a firm in Seattle called Magus. He's going to talk to us about the structural engineering safety field, request field. We still have to pin down on one that they call structural engineering. It's not every day you get to really see kind of a marquee structural engineer discuss a